Okay, so the very, very last part of this topic will be to look at a couple of past paper questions from the IB. As normal, we'll look at one multiple choice and one short answer. So the multiple choice question from the May 2018 paper is one about a gas sample and the emission spectrum. The emission spectrum of hydrogen gas, and you'll remember the emission spectrum is basically bright lines on a black background, because it's the light rays being given off by electrons moving to the ground state after being excited. And it just gives two arbitrary lines. It calls them X and Y in order of increasing wavelength. And it then says, hey, for some unknown reason, you're looking at this emission spectrum while you, the observer, are moving away from the gas sample. What are the correct shifts X star and Y star for the spectral lines X and Y? So, how to answer this? Well, you're moving away. If you're moving away, if the separation is increasing, it doesn't matter if it's you moving away or the source moving away from you, that's going to be a redshift. Redshift is increasing wavelength, so X star and Y star will be of increasing wavelength compared to X and Y, and the only two possible options there are C and D. So moving away equals redshift. So is it going to be C or is it going to be D? Well, there we look at the equation. And the equation says that the change in wavelength, the increase in wavelength, is basically proportional to V multiplied by, the wavelength multiplied by V over C. Now V over C is constant here, so it's just going to be proportional to the wavelength. So the bigger the wavelength, the bigger the change in the wavelength, and therefore the only valid answer to that is C, because X being the smaller one has the relatively small increase, Y being a larger wavelength has a larger increase. Okay, this is just part of a larger question, this 2015 question, so it's why we're looking at part B, but all that we need to know is here. So you have an X-ray source which for some bizarre reason you've put on a turntable, and it's emitting radiation of wavelength 7.5 nanometers. And as it goes around, the maximum shift, maximum change in that wavelength is the rather small 0.50 femtometers. Now that's not a prefix you come across every day, but it's in the data booklet. The distance between the source and the detector is large in comparison to the diameter of a turntable, so we don't really have to worry about sort of the angles. So determine the speed of a point on the edge of a turntable. Well, it's X-rays, so it's electromagnetic radiation. Therefore, the relevant equation is the EM Doppler shift equation. You're talking about wavelength, so let's just keep the wavelength side to it. And you've got delta lambda. Delta lambda, you know, is 0.5 femtometers. Lambda is 7.5 nanometers, and you know C because C is C. So I guess what you don't know is V. So we can have that equation in there. We can rearrange for V. V equals delta lambda multiplied by C divided by lambda. We can plug those numbers in using the appropriate standard form. So femtometers is 10 to the minus 16 multiplied by the speed of light divided by 7.5 nanometers, which is 10 to the minus 9, will give us a value, the speed of about 20 meters per second. So 20 meters per second will give you a frequent wavelength shift of half a femtometer. Okay, so that was fine. What were the assumptions you made in your answer to B part 1? It's actually quite a tricky one. If you don't know it, I think. I mean, the assumptions that you can is that you can use this equation. So what assumptions are that you can use this equation? Well, you might say it's the equation for light, but I actually did mention this in the previous video. Is really the assumption is that the velocity of the source, the velocity that you're measuring in part 1, is much, much less than the velocity of the wave in this medium, i.e. the speed of light. So that the speed of the X-ray equals the speed of light, I mean, I quibble if that's an assumption. I think you're a DP physics student, you should know that. Although, technically, c is the speed of light in a vacuum, and we haven't said that this is happening in a vacuum, but maybe that's our assumption. We're assuming that this is happening in a situation which is, if not a vacuum, is one where the speed of light is very close to the speed of light in a vacuum, which it is, if it's air. So that the speed of the X-rays is about equal to the speed of light in a vacuum, and that the speed of the turntable is significantly less than the speed of light in a vacuum. Those are the two assumptions which you could make, and which together would give you the 1 mark that is all that's on offer for this part of the question. Okay, well done. That has now finished the topic, finished the whole topic. If you haven't done so far, get out and start practicing some questions on your own.